In the diagram below of circle O, tangent EC is drawn to diameter AC, and chord BC is parallel to secant ADE, and chord AB is drawn. Prove the proportion that BC over CA is equal to AB over EC. So let's mark up a diagram based on the given information here. Just based on the givens that BC is parallel to ADE, I'm just going to indicate that with some parallel markings. And immediately I notice that there are two alternate interior angles. So I have these two angles that are going to be congruent. Something else I notice is that the chords AB and BC that are drawn in, they are inscribed in the semicircle. There's a theorem, right? If you have an inscribed angle inscribed inside of a semicircle, the inscribed angle will be a right angle. Or I think an alternative way of stating it is that the inscribed triangle in a semicircle will always be a right triangle. Another thing I notice, since EC is tangent to circle O at point C, and AOC is the diameter, the angle formed between the tangent and the radius or diameter will always be a right angle. So looking at the diagram markings that I have made thus far, check this out. I have triangle ABC will be similar to triangle, let me see, what is this? This is ECA. And why is that? Well, that's because I have two angles that are congruent that I've marked up. And once I have these two triangles are similar, I can then prove those sides proportional, because those sides spring directly from those two similar triangles there. All right, so that's the game plan. So let's put this in writing, okay? So right now, I have the statement and reason chart already made. That BC is parallel to ADE, and that AOC is the diameter. I forget to mention that EC is tangent to circle O. Okay, and this is also the part of the givens. All right, so based on just the given information there, one of the first things that I had mentioned was the alternate interior angles. So I'm going to say BCA, angle BCA, is congruent to angle EAC, or CAE. And this is because of alternate interior angles. Whoops. I did not mean to go to the next page. Alternate interior angles are congruent. Okay. And then the next thing that I said was angle ABC is a right angle. And the reason for that is inscribed angle in a semicircle is a right angle. All right, and then the next thing I said was angle ACE is a right angle. And the reason for that is tangents form right angles with diameters of a circle. Okay? And since those two angles that I mentioned in line 5 and line 6 are right angles, then I can then say that angle ABC is congruent to angle ACE. And why is that? Well, that's because all right angles are congruent. And why is that important? Well, that is because we need to show that there are two angles congruent here. So in line 4 and line 7, we've shown that there are two angles that are congruent, two corresponding angles that are congruent. So then we can say that triangle, what is that? Triangle ABC will be similar to triangle ECA. And this is because of angle-angle theorem. And the last thing that we have to do is actually just to set up that proportion, right? Because look, BC to CA, right? So BC to CA, so BC to CA is equal to AB, and look, it corresponds, AB to EC, right? So the last thing is BC to CA is equal to AB to EC. And the reason is, I need a little room to write this, corresponding lengths of similar triangles are proportional. So there you have it. This is the full proof right there. Let me just zoom in a little bit more.